Welcome to section 19.1. 19.1 is a section about balancing equations and looking at how when we combine two reactants or multiple reactants and we get products on the other side of that reaction and how we're going to represent those in different ways. Today we're going to take a look at 3 different ways to represent a chemical reaction. But before we do that, we want to just review a couple topics that we've had before in the past, just to make sure you're aware of some vocab that you have seen before. If we look at your paper, we see an equation there, and I want to spend a few minutes going over that equation. We have CH4, we have 2HO2, and that's yielding CO2 and 2H2O. Okay? The thing that I want to take a look at is the different numbers that we have represented in this equation. And I want to make sure that you're familiar with the vocab. The first number I want to take a look at is this guy right here. That is called a subscript. Okay? That subscript is indicating how many atoms of that element we have in this formula equation. So if we look over here, okay, it's CH4. What this is saying is we have 1 carbon, because there's no subscript, which tells us there's 1, and we have 4 hydrogens. So we have 1 carbon bonded to 4 hydrogens, and those we've done molecular diagrams, so you know those 4 hydrogens are kind of surrounding that carbon. Okay, in this case we have 2 oxygens in 1 molecule. Over here we have 2 oxygens in CO2, and we have 2 hydrogens in H2O. Anywhere you don't see a subscript, you're assuming that there is 1. Okay, the other number that you aren't as familiar with but still familiar with is this number right here. That number is called a coefficient, and that's your first blank on your worksheet there. A coefficient is telling us how many molecules are present in that equation. And what that does is it provides a ratio for us. If we look if we look at our 2 reactants, we have let's get a different color here. We have this reactant here, and we have this reactant here. We have oxygen, we have methane. Okay? What this is saying is that when oxygen combines with methane, they're going to basically react in a 1:2 ratio. 1 carbon, 1 CH4 for every 2 O2. Okay? And that's what those coefficients are there for. But just make sure that when I say coefficient, you know that I'm referring to this number, and when I say subscript, you know what I'm referring to this number. Okay, so the first type of representation we'll look at is the word equation. The word equation would be exactly what it sounds like. If we took words and wrote them out to represent what is happening, oxygen, in the equation. Okay, yields, we have carbon dioxide, and water. Sorry for the shaking around there. Okay, that is considered a word equation. Okay, that word equation is basically just words showing what's happening. If we take this word equation and we substitute the words for the formulas, so for instance, the formula for methane is CH4. So we took CH4 plus the formula for oxygen is O2. The formula for carbon dioxide is CO2. Okay, and we have H2O. Okay, so this up here is our word equation. This is our formula equation. And basically the formula equation is just taking those formulas and turning them into, or taking those words and turning them into formulas. So far, we have 2 ways to represent a chemical reaction. Okay, we have a word equation and we have a formula equation. The third way is to take that formula equation and make it into a chemical equation. The way we make it into a chemical equation is we are going to take those formulas and write them in the correct ratios, okay? The ratios that they belong in order to show that the reaction is balanced and basically represented by what actually happens in the real world. So this last example here would be an example of the formula, or the chemical equation. Okay, and the reason is because of our coefficients. The coefficients here are showing the actual ratios that methane is combining with oxygen, the actual ratios that carbon dioxide is combining with H2O, and the actual ratio of the reactants that will get to the products. Those correct ratios indicate that they are balanced and that it is a chemical, in fact, a chemical equation, opposed to a formula equation, which is not balanced, even though the formulas are used, and a word equation, which is not balanced, even though the correct words are used to indicate what's the chemicals that are combining. Okay. The other thing we need to talk about when thinking about um, your about chemical reactions is the different ways we can identify that a chemical reaction is taking place. There are 4 that I want you to know. Some of them pretty much indicate a chemical reaction all the time. Some of them might indicate a chemical reaction, but not necessarily does. The first one is if you produce heat and light. If you're producing heat and light, there's a good chance that a chemical reaction is taking place. The second one would be if we're producing a gas. Okay. Um, Sometimes we can't see the gas production. Other times when the reaction is happening in solution, you can see the gas being shown in the form of bubbles. Okay, if you see bubbles in a solution, that's usually a pretty good indication that a gas is being formed. The third way that we know is if we produce something called a precipitate. A precipitate is a solid that is produced during a chemical reaction. A lot of the times this will happen when you combine 2 solutions and you get a solid that will settle out of the solution at the end of the reaction. And the third way is if you possibly have a color change. Now, a color change does not always indicate a chemical reaction. For instance, if I mix together yellow and blue food coloring, you'll see green and you have a color change, but that's not really a chemical reaction. Okay. Um, and so be careful with the color change, because most of the time that would indicate a chemical reaction, but not always. The last topic that I wanted to cover today is the things that must be true about a chemical equation. Okay, or a chemical equation. First of all, the chemical equation must have known facts. Okay, you can't start basically you can't in basically take 2 reactants and combine them and want to make up some product that's never been seen in the natural world before. The things that you represent in a chemical equation must have been observed at some point. Okay, which kind of is a sub point to that is your second point, which is it must have known formulas. Okay, correct formulas. You can't change H2O to H4O2. Okay, even though it's the same ratio, it's not the same chemical. It's not water. Okay, H2O is water, and it has to have that correct formula. And the third thing is that the law of conservation of mass must be satisfied. In other words, what you begin with in terms of mass has to be what you end with in terms of mass. We cannot destroy mass. We cannot create mass out of nowhere. So what we end with has to be what we started with. Okay? And if you think back to the short little video clip you watched, you might be asking yourself, okay, well, Mr. Hess said we lost like 2 grams of substance when we did the baking soda and vinegar. Well, what's actually happening there? Well, if you think to the evidences of a chemical reaction, one of those evidences is the production of gas. Okay, and that production of gas is going, in this situation, since it wasn't enclosed, was released into the atmosphere. Okay, so we didn't really lose mass or destroy mass. We simply just released gas, and therefore our product was a little less than our combined reactants. Okay. That's pretty much what I wanted you to get out of this session. I want you to know the 3 ways to represent a chemical reaction, which are word formula, or word equation, formula equation, and chemical equation. And I want you to know the 4 evidences of a chemical reaction. And I want you to know the 3 things that all chemical equations must satisfy. Okay, so make sure you know that stuff. Make sure you know those things and go on to the activity that is provided for you on this worksheet. We'll see you next time.